can start.
Hi, everyone. Sorry for the problem with my mic. My name is Luca, and I'm presenting the work Mapping Across Relational Domains for Transfer Learning with Word Embeddings-based Similarity. So in this work, we focus on statistical relational learning, which combines elements from statistical and relational modeling to relational learning. As traditional machine learning models, SRL models also assume training and test data must belong to the same feature space and must have the same distribution. If those distributions differ, a new model must be trained using newly collected data. Relational dependence networks have the capacity of expressing and reasoning dependence among attributes of entities. So in a RDN, each predicate Y is associated with a conditional probability distribution given its parent values, here represented as PA. In this work, we use RDNB, which proposes to represent each conditional probability distribution in a RDN as a weighted sum of regressional models using gradient-based boosting. And to address the problem of training and test data to differ on distribution, we'll apply transfer learning, which is a technique that allows machine learning models to use the knowledge previously learned in a source domain and apply this knowledge to learn a new model in a target domain. So we no longer train models from scratch, as we would do in traditional machine learning processes. So as SRL models have a vocabulary in this work, we are interested in transferring vocabulary from a source domain into a quite different target domain. So the proposed algorithm is named TransBooster, and it has four main components: preprocessing, compute similarities, mappings, and then it applies theory revision to try to improve the model's accuracy. So the preprocessing consists of 4 steps. The first step is segmentation. As predicates can be formed by 1, 2, or more words, we must segment them so they can become a small phrase, like athlete plays for team, which has 4 words. As in our data sets, we have some abbreviations. So we have a pre-built dictionary to replace abbreviations by its full form, like TA, which stands for teaching assistant. The third step is representation. As we are focused on transferring vocabulary, we want also to take advantage of the context in which those words must appear. So we use a pre-trained fast text script-grand model trained on Wikipedia Corpora. The next step is concatenation. As one of the similarity metrics can deal with n-dimensional vectors, we must concatenate them, so we avoid information loss. So we treat each term as a dimension, and if a term doesn't belong to a predicate, it's represented by a new vector. So we no longer want to train a model from scratch, so we use the structure learned in the source domain and replace each predicate in the source domain by its corresponding mapping in the target domain. So in this case, actor will be replaced by student, director by professor, and movie by publication. So we are only mapping predicates of the same arity. And the algorithm continues on learning. This is just the starting point. So it continues on learning to fit the target data. Doing revision, we can either prune a node to make the theory more general or expand the nodes to make the theory more specific. We evaluate TransBooster using cross-validation, so results are averaged over any runs. The first experiment, we use 1-fold for training and n-1 for testing, and in the second, we use traditional cross-validation. To compare performance, we use the following measures: conditional log likelihood, area under the ROC curve, area under the PR curve, and training time. We did not consider time to load the pre-trained model, but we didn't consider time to compute similarities. We use 6 available data sets. In this presentation, I'm presenting 4 experiments of 6, so the last 2 are in the paper. And we subsample negatives examples in a ratio of 2 negatives for 1 positive when training, and we use it all examples for testing. We compare our results with learning from scratch.
4 minutes, Paes.
Okay, thank you. Which is RDNB itself, and TreeBooster, which is another transfer learning based framework, which performs exhaustive search to find adequate mappings, and then it applies theory revision to try to improve the model's accuracy. We use a Euclidean distance, soft cosine similarity, and word movies distance to compute similarities. The first pair are IMDb and Cora. So in our tables, the bullet indicates results with no theory revision, only mapping and parameter learning. The star symbol indicates when transbooster is significantly better than tree-booster, and the diamond indicates that the difference between transbooster against RDNB results are significantly better. So when transferring from IMDb to Cora, we don't get significantly better results. However, the results are competitive to both baselines, and our algorithm is less time consuming than learning from scratch. When we don't apply theory revision, it results in negative transfer. This is due to IMDb has 3 predicates in the source structure. 2 of them are unary predicates, and Cora has no unary predicates. So we can just map one predicate of arity 2 to another of arity 2. So theory revision is really important here. When transferring from Cora to IMDb, we have significantly better results for ILC-ROC when used soft cosine and world movies distance. And when we don't apply theory revision, it underperforms both baselines. When transferring from IST to Twitter, we get significantly better results for ILC-ROC when using soft cosine. Also, our algorithm is less time consuming than learning from scratch, and our results are competitive with both baselines, even when we don't apply theory revision. When transferring from Twitter to IST, it underperforms for ILC-ROC when using the Euclidean distance, but it outperforms for ILC-PR and underperforms for soft cosine, and also is less time consuming when we are using the Euclidean distance, less consuming than learning from scratch. When we don't apply theory revision, it's significantly better when for CLL, but it underperforms.
2 minutes, Thais.
Okay. For ILC-ROC. So then the second experiment, we incrementally increase the amount of target data. So training data is shuffled and divided into 5 sequence parts. So when transferring from IMDb to Cora, it underperforms both baselines. When transferring from Cora to IMDb, it outperforms tree-booster, and the results are competitive to learning from scratch. When transferring from IST to Twitter, it underperforms tree-booster for ILC-ROC, and results are competitive to learning from scratch. And for ILC-PR, it outperforms tree-booster except for when we're using 4% of the training data and Euclidean distance. And it underperforms RDNB when we're using, again, Euclidean distance and 80% of the training data. When transferring from Twitter to IST, it underperforms tree-booster and outperforms RDNB for ILC-ROC, and for CPR, it underperforms tree-booster except when using 80% of the training data and world movies distance, and it underperforms learning from scratch when using 20, 40, and 80% of the target data for soft cosine similarity. So our experimental results show that mapping by similarity has a good performance and can be less time consuming. However, it depends on the pair of data sets. So it remains a future investigation to understand whether or not to transfer. And also the effect of the data in which the embedded word training matters. So we believe that if we change the context in which those words appears, we have different mappings. The main contribution of this work is I almost finished. The proposed mapping component, which can also be applied to different and more general relational models. And one possible future direction is to select the top n most similar predicates to proceed with the mapping. So thank you very much for the attention.